Welcome to G Fun Facts Online. Our planet is wrapped in an invisible shield, a magnetic field that protects us from dangerous space radiation. But this shield has a problem. There's a massive, growing dent in it, an area of profound weakness stretching from South America out over the Atlantic. It's called the South Atlantic Anomaly, and it has scientists watching closely. Because over the last 200 years, Earth's entire magnetic field has weakened by about 9%, and this anomaly is the most dramatic symptom. It's expanding, drifting, and now it appears to be splitting in two. So what is this invisible dent? What's causing it? And could it be a warning sign that our planet's magnetic poles are getting ready to flip entirely? Let's unravel the mystery. To understand the dent, we first need to understand the shield itself. Earth's magnetic field isn't created by a giant bar magnet in the middle of the planet. Instead, it's generated by a colossal engine 800 miles beneath our feet in the Earth's outer core. Imagine a vast ocean of molten iron and nickel, as hot as the surface of the sun, constantly churning. Hotter liquid rises, cools, and sinks, creating massive turbulent currents. But here's the key ingredient: the Earth's rotation. This rotation adds a twist, organizing the flowing liquid iron into spiraling columns, a bit like how hurricanes form in the atmosphere. Because this molten iron is electrically conductive, its movement generates powerful electrical currents. And as basic physics tells us, moving electrical charges create a magnetic field. It's a self-sustaining process called the geodynamo. The magnetic field influences the molten iron, which in turn generates more current, which reinforces the field. This cosmic engine has been running for over 4 billion years, protecting our atmosphere and water from being stripped away by the solar wind and allowing life to flourish. But this engine is chaotic, and that chaos is what gives us the South Atlantic Anomaly. This is the region where our magnetic shield is at its absolute weakest. Globally, the field's strength averages around 32,000 nanoteslas. Inside the anomaly, it can plummet to just 22,000. This weakness is a direct window into messy processes happening deep inside our planet. The main reason for the anomaly is that our planetary magnet is not perfectly centered. It's tilted by about 11 degrees from our planet's spin axis, and its center is offset from Earth's geometric center by nearly 500 kilometers. This asymmetry causes the Van Allen radiation belts, rings of high-energy particles trapped by the magnetic field, to dip closest to Earth's surface, right over the South Atlantic. Here, the inner belt can descend to just 200 kilometers altitude, right into the orbital path of many satellites. But what's causing that fundamental asymmetry? Evidence points to a bizarre, colossal structure at the boundary between the liquid core and the rocky mantle above it. It's called the African Large Low Shear Velocity Province, a sort of giant superplume of unusually dense, hot rock. Scientists believe this massive feature disrupts the smooth flow of molten iron in the core, directly beneath it. This disturbance creates what's called a reverse flux patch, a localized area where the magnetic field lines actually flow into the core instead of out. This deep-seated flaw is what we see on the surface as the South Atlantic Anomaly. And this anomaly is not standing still. Data from satellites, especially the European Space Agency's SWARM mission, shows it's evolving rapidly. For starters, it's growing in size and drifting westward at about 20 kilometers per year. At the same time, the weak spot is getting even weaker. Between 1970 and 2020, the minimum field strength inside the anomaly dropped from around 24,000 nanoteslas down to 22,000. But the most startling recent discovery is that the anomaly is splitting apart. What used to be one large valley of magnetic weakness has begun to fork into two distinct lobes. One center of weakness remains over South America, but a second, rapidly developing minimum has appeared to the southwest of Africa. This means the situation is becoming more complex, with multiple distinct weak zones for spacecraft to navigate. It's a direct sign of the chaotic, shifting dynamics happening at the core mantle boundary, nearly 3,000 kilometers below our feet. While the anomaly poses no direct risk to us on the ground, it's a huge and growing hazard for our technology in orbit. Satellites in low Earth orbit, including the International Space Station, pass through this region regularly. Inside the anomaly, they are bombarded by high-energy protons from that dipping Van Allen belt. This radiation can cause all sorts of problems. It can trigger what are called single-event upsets, where a particle hits a memory chip and flips a bit from a 0 to a 1, causing data corruption or computer crashes. In fact, astronauts on early space shuttle missions reported their laptops would frequently crash when they flew through the SAA. Over time, this radiation can also cause permanent physical damage to microelectronics, shortening a satellite's lifespan. It can also create noise in sensitive scientific instruments. The Hubble Space Telescope, for example, has to suspend its science observations every time its orbit takes it through the anomaly to avoid data corruption and protect its delicate sensors. Many satellite failures have been blamed on the SAA, but perhaps the most dramatic example was the loss of Japan's Hitomi X-ray astronomy satellite in 2016. The $250 million mission was lost just a month after launch. The fatal chain of events began when its star tracker system, which tells the satellite its orientation, malfunctioned while passing through the South Atlantic Anomaly. Believing it was spinning when it wasn't, the onboard computer fired the thrusters to correct the non-existent spin. This sent the satellite into a real, uncontrollable, high-speed rotation that literally tore it apart. To avoid this fate, operators often power down sensitive instruments when passing through the region. Even astronauts are affected. Those on the ISS have reported seeing strange flashes of light with their eyes closed, a phenomenon called phosphenes, caused by cosmic rays passing directly through their retinas inside the anomaly. So how do we know all this about an invisible force? We rely on an incredible combination of observation and modeling. Our eyes in the sky, our missions like ESA Swarm constellation. This trio of identical satellites orbits the Earth, making hyper-precise measurements of the magnetic field. Two fly side by side at a low altitude to map fine-scale details, while a third orbits higher up to provide context. This allows scientists to separate the main field from the core from other magnetic sources. The data from Swarm, along with historical records, is then fed into complex computer models. You have the International Geomagnetic Reference Field, or IGRF, which is the standard model used for everything from your smartphone's compass to directional oil drilling. Then you have higher resolution research models, like the Chaos Model series, which uses the very latest satellite data to track rapid changes. It was the Chaos model that first clearly identified the splitting of the anomaly. And by digging into historical ship logs and observatory records, models like GUFM1 have reconstructed the field all the way back to 1590, showing us that the current weakening trend has been happening for centuries. Together, these tools give us a four-dimensional map of our magnetic shield, tracking its structure in space and its evolution through time. This brings us to the ultimate question. With the field weakening and the SAA growing, are we heading for a full geomagnetic reversal, where magnetic north and south completely flip? The geologic record tells us this is a normal, if irregular, part of our planet's life. By studying the magnetic alignment of minerals in ancient volcanic rocks, we know the poles have flipped hundreds of times. The last full reversal happened about 780,000 years ago. Since the average time between flips is highly variable, some scientists suggest we might be overdue. The process isn't instant. It can take thousands of years, during which the main field weakens dramatically, and multiple local north and south poles might pop up all over the globe before it settles into a new, reversed orientation. Some studies propose that the South Atlantic Anomaly, with its reverse-flowing magnetic field at the core, could be the seed of a future reversal, a spot of opposite polarity that could grow and take over. However, many other experts are not convinced. They argue that the current weakening might just be a temporary fluctuation, something called a geomagnetic excursion. This is where the field weakens and shifts, but then snaps back to its original state without a full flip. The La Chape excursion, around 41,000 years ago, was one such event. Right now, there is no scientific consensus. The SAA could be the start of a planet-wide flip, or it could be a dramatic but ultimately temporary feature that will eventually fade. So let's say a reversal does happen. It wouldn't be an apocalypse. Our thick atmosphere, not the magnetic field, provides the primary shield against the most harmful radiation. The fossil record shows no link between past reversals and mass extinctions. But the consequences for our modern, technological society would be severe. With a globally weakened shield, the harsh radiation environment, now mostly confined to the SAA, would expand. Satellites would be constantly bombarded, leading to widespread failures. GPS, global communications, weather forecasting, all could be crippled. Our power grids would also become extremely vulnerable. A major solar storm, which our current field mostly deflects, could induce massive currents in transmission lines, frying transformers and causing continent-wide blackouts that could last for months. Finally, background radiation levels on the surface, especially for frequent flyers, would increase, potentially leading to a higher global risk of certain cancers. There are even more speculative links to climate, with some theories suggesting that increased cosmic rays could alter cloud formation, potentially leading to a global cooling effect. These connections are still being researched, but they highlight just how deeply the magnetic field is intertwined with the entire Earth system. The South Atlantic Anomaly is more than just a strange flaw in our planet's armor. It's a live laboratory, giving us a rare glimpse into the colossal engine churning deep within the Earth. It's a stark reminder that we live on a dynamic world, protected by a shield that is in a constant state of change. The ongoing weakening of the field and the strange splitting of the anomaly is one of the great geophysical mysteries of our time. While we don't know if our magnetic shield will eventually stabilize or continue towards a full reversal, our ability to watch it, model it, and understand it is growing every day. This knowledge is crucial. It's essential for protecting the technological backbone of our modern world and for understanding the long-term habitability of our home planet. The story of the South Atlantic Anomaly is the unfolding story of our planet's invisible shield, a force that has protected life for billions of years and whose future we are finally beginning to see.